Welcome to another episode of James Explains, and again, we're taking a look at another one of Matt Parker's maths puzzles. This puzzle is the optimal ellipse, where we find the spacing between two foci that will give us the largest area when traced with a 28cm string. I still haven't got around to learning the 3 blue, 1 brown animation library yet, and I couldn't work out how to animate connected lines in PowerPoint, so you'll just have to use your imagination for this bit. Firstly, it should be obvious that as the distance between the foci approaches 28cm, the semi-minor axis shrinks to 0, so going too high for the distance will reduce the area of the ellipse. However, I've seen a lot of suggestions that having no space between the foci would give the greatest area, but that's not exactly true. Firstly, we will need to know how we calculate the area of the ellipse based off the space between the foci. Our two main dimensions are the semi-major axis, or width, and the semi-minor axis, or height. These terms don't exactly match, but I'll use them interchangeably in this video. Starting with the semi-minor axis, we can see that this is found at exactly the halfway point between the two foci. If we look at just one half, we can see that half the length of the string would reach from one focus to the end of the semi-minor axis, and half the gap between the foci would reach to the center of the ellipse. This should be obvious that this forms a right angle triangle. We can use Pythagoras' theorem to determine that the semi-minor axis will have a height equal to the square root of half of the length squared minus half of the spacing squared. In this case, we can simplify this height to the square root of 196 minus x on 2 squared. Next, we need to find the length of the semi-major axis. This one is a bit harder to visualize because the lines lie atop one another, but we can determine that the width from the center to one focus is x on 2, and the remaining width would be 28 minus x on 2 all over 2. This gives our semi-major axis a total width of x on 2 plus 28 minus x on 2 over 2, which can be simplified as 14 plus x on 4. So now to work out the area of the ellipse. We take the value from our semi-minor axis and the value for our semi-major axis and drop them into this formula. We can say that the area for an ellipse with a string of 28cm is pi times the value for the semi-minor axis times the value for the semi-major axis. So to work out the puzzle, we would just need to determine the local maximum value for this equation. However, let's look at the case where x equals 0 to prove that this is not the greatest possible area. We can say this would form a circle with a radius of half the length of our string, or 14cm. But what we want to do is look at what happens when we start to separate the foci very slightly. The semi-minor axis will be 14 minus a small amount, and the semi-major axis will be 14 plus a small amount. Starting with the width of the semi-major axis, which we have given the value of 14 plus x on 4, as x starts to increase from 0, we can see that the change to this width is x on 4, which is a linear increase in width. Therefore, even at small values, the change would be notable. Next, we want to know what happens to the semi-minor axis at the same time. We have a value that can represent it, but rather than use the equation, we could make some other observations about what happens. When the foci start to separate very slightly, we start with a far lesser change in the value of the semi-minor axis. The best way to visualize this is by remembering that this height is represented as a right angle triangle, where we can take the angle at the top of the triangle, the semi-minor axis is the adjacent side, and we have a fixed value for the hypotenuse. Using these values, we can look at what happens to the cosine of this angle as it starts to increase. When there is no gap, the ratio is 1, and the semi-minor axis is equal to half the length of the string. As we rotate through 90 degrees, the ratio is now 0, which is where the ellipse has become so wide that it has no height. What's important to note here is at the start of the transition, as we increase the angle very slightly, at first, we only have a negligible change in the ratio, meaning we only have a negligible change to the height of the semi-minor axis. With a small yet notable increase in the semi-major axis and a negligible decrease to the semi-minor axis, it is therefore obvious that the area of an ellipse with zero gap would be less than the area of an ellipse with a greater than zero yet still small gap. So, somewhere between an ellipse with no gap between the foci and one with a huge gap between the foci, there must be an ellipse with a greater area than either of these two shapes. When the formula for the area of an ellipse that we found earlier is graphed, we get this output. You can clearly see that at zero gap between the foci, we have a local minimum area, so that is definitely not the optimum ellipse. You can see that this chart has local maximum at roughly an x value of 10 centimeters and a second at -10. This represents the highest possible area for an ellipse, so taking this value for a separation between the foci will give us the optimal ellipse. This should demonstrate that whilst having no space between the foci might intuitively feel like the best option, just going with intuition or gut feeling is not always the best way to find a solution to a puzzle. There's nothing I can say, it's like a total ellipse of the heart. If you want to see the original puzzle, or many others like it, visit thinkmaths.co.uk/mathspuzzles to find out more. If you have any questions, comments, compliments or complaints, or if you found an error in my video, which is pretty normal for me, make sure you let me know in the comments down below. And as always, thanks for watching.